We're going to talk about exponential functions. So exponential functions, we did exponents in the last chapter. We did radicals. Now we're talking about functions. And it's not just like I have an x to a square. We've done that. That's quadratics or, cubic or whatever. We're talking about when my variable is in my exponential place. All right? And so when your variable is in your exponential place, then you have an exponential function, all right? That's when you have an exponential function. Y equals x squared is not an exponential function. That's a quadratic. But y equals 2 to the x, that's an exponential function. I have an x in my exponent place. So you'll notice that it's in this form. You will always have your exponential functions in this form. Y equals ab to the x. A is just a coefficient. B is your base, and x, of course, is your variable, which is your exponent. Your B will help you determine what's called the growth factor, your growth factor. And actually, we're going to talk about decay as well. What you'll notice about an exponential function is that it shoots up. So if you look at example 1 here, they've given us an exponential function, y equals 2 to the x. My x is in my exponent place. It is an exponential function. And you'll see the graph. Now, if I just had the function something like y equals 2x, that's not an exponential function. That's a linear graph, right? With a y-intercept of 0 and a slope of 2, right? 2 over 1. So if I go, and it's a pretty steep slope, up 2 over 1, you'll notice it tracks fairly well, and then all of a sudden it stops tracking, right, with my exponential. So what happens with linear is this nice steady growth. Linear will grow at the same exact slope all the time. Exponential shoots up, all right? Exponential shoots up. And so exponential grows much faster. It doesn't seem like it at first necessarily, but it does. It grows a whole lot faster than a linear growth. Linear is steady and it's always going to go up at that rate. But exponential all of a sudden shoots up. And so you'll hear the term, it's growing exponentially. That means it's not just steadily growing, it's actually exponentially growing, which means it's going to grow faster. Decay is going to decay faster when it's exponential decay. And the way you can tell if it's growing or if it's decaying is just by that coefficient. So we're going to do some examples with that. I don't want you to know how to graph them necessarily, but I want you to be able to picture the difference between a linear and an exponential growth. Exponential is going to curve and then shoot up or shoot down depending on if it's growth or decay. All right, so let's look at one of the examples. Example 2, page 423. One type of exponential growth is population. Population grows exponentially, not linear. Refer to the graph. In 2000, the annual rate of increase in the U.S. population was about 1.24%. Find the growth factor for the U.S. population. Suppose the rate of the increase continues to be 1.24%. Write a function to model the U.S. population growth. All right, the growth factor. So they have given us 1.24% as the annual increase. And so if I'm looking for the growth factor, I am always going to start out with, so B is going to be my growth factor in that little y equals AB to the x. B is what we're looking for, our growth factor. It is always going to be 1 plus my rate of increase. So my rate of increase here is 1.24%. Now I cannot add 1.24% and 1. I have to make 1.24% a number in standard form. How do I write that in standard form?
0, 1, 2, 1.
Yeah, I need to move that decimal place over 2 places. All right. So I have 1 plus 0.0124. So my growth factor is 1.0124. Growth factor. All right. Write a function. Now, my exponential functions, we just said, are always in this form right here. Y equals a b to the x. Y equals a b to the x. All right. And so I now know what my b is. I just solved for it. Y equals a b, 1.0124 to the x, all right? Now, I need to figure out then what my initial condition is, all right? And so they have picked a y value and an x value here. So if I look at my y and x value, 2000, we're talking about from 2000, we're going to use that as our initial, 0. 281 is what it was in 2000. So if I look at 2000, 281 is what it was in 2000. And we're not going backwards, we're starting from here going forward. All right, so if I have to define this, I have to tell you that's what I'm doing. And so I would say something like the year 2000 equals an x value of 0. All right, that way I know if I try to solve for 2010, I'm going to use 10, right? So anytime you're talking about years, they'll say, 1980, that's your initial year. That's your year 0. And so 1981 would be 1 and 1982 would be 2, so that you don't have to put in the whole 2000, all right? So we're just going to say, we're going to say that 0 represents the year 2000. So then 5 would represent the year 2005. 10 would represent the year 2010, right? Does that make sense? And so I'm going to plug in then an x value of 0, and my y value then would be 281. So this is basically an xy. This is my x, we're going to say that's 0. This is my y, 281. So I have an xy of 0, 281, xy value. And so what I'm going to do is I'm going to take those xy values and plug them in here so I can solve for a. So I'm going to say then y is 281 equals a 1.0124 to the 0. What's any number to the 0 power? All right, so this is just 1a equals 281. So I have my a. So my function then, which is what they want me to they want me to set up, is y equals 281 times 1.0124 to the x. This would be my exponential function for the growth population based on what we have right now. All right, let's go over these. Predict the population in 2015 to the nearest million. You should have gotten about 338 million. All you had to do is plug it into our formula. Why could your prediction might be not valid? That could change population. Just birth rate could change, death rate could change. Anything could happen to affect population. And so because it's a prediction, anything can affect your prediction. It is just a fact that the growth factor could change for some reason. Some reason could affect the growth factor. And so then they said, let's suppose it does change. Let's suppose it increases to 1.4 instead of what we had at 1.24. So your new formula should have looked like this. It should have been y equals 281. And you should have had 1.014 here to the x. And then when you plug that in with 15 years, you would have gotten about 346 million. All right, so when it says write an exponential function, y equals ab to the x is the standard form of an exponential function. And they want it for a graph that includes the 0.22 and the 0.34. So they have given us two x's and y's. We have a 2,2 as an xy. We have a 3,4 as an xy. And so we are going to take this function here and we are going to plug in our x and y and we are going to solve for these functions. So my x and y are 2 and 2. So I have y equals a b to the x. Y equals a b to the x. Then I have 3 and 4. So I have y equals a b to the x. All right. Now, I need to solve, I have two variables here in two different equations. And so what I want to do is I want to get these equations equal to the same variable. And that way I can then set them equal to each other and solve for one of the variables and solve backwards. So when I have something like this, the easiest variable to solve by itself is going to be a, always, because it's always going to be b to some power. All right, so this first equation I'm going to divide by b squared. right? And I will get A equals 2 over B squared. I'm going to do the same thing in the second equation. Divide by B cubed. And here I will get A equals 4 over B cubed, right? And now I have two equations that equal A, which means I can set those two equations equal to each other. I can say, well, 2 over B squared should equal 4 over B cubed. All right, I want all my B's on one side, all my numbers on the other. So to do that, I am going to multiply both sides by this B cubed here, okay? And on the right-hand side, my B cubed will cancel, all right? And on the left-hand side, just my B squareds will cancel. So I'll take 2 out of there and 2 out of there, right? So I get 2B equals 4. What does B equal? B equals 2. And then I can take that and plug that back into either equation to solve for A, right? So if I take the 2 and plug it back in here, I get A equals 2 over 4, or A equals what? And the same thing would happen here. I get 4 over 8, right? It would be equal 1/2. And so to write that equation, I'm going to say, to write the equation, I'm going to leave my Y and I'm going to leave my X. I'm going to fill in my A and my B. So Y equals A, that's 1/2, times B to the X. And that will be my function that goes through those 2 points. My exponential function that goes through those 2 points. Yes, I will take 1/4. Yeah, I would have left it as 1/4. I would have put 0.25 personally, but that's just me. Yeah, you can definitely leave it as 1/4. So let's look at this. We have Y. So we'll have 4 equals AB to the second power. And we have 16 equals AB to the third power. So when I get A by itself, I will get A equals 4 over B squared. And A equals 16 over B cubed. I'll set those equal to each other. 4 over B squared equals 16 over B cubed. If I multiply both of these by B cubed, I am going to get that 4B equals 16, so B equals 4. And if I plug 4 back in, I will get A equals 4 over 4 squared, or 16, which is 1/4. So when I rewrite the whole thing, I will get Y equals A, which is 1/4, times B to the X. But if you are just looking at the function itself, you can look at the B. And you can tell if the B is going to be growth or going to be decay. The B is going to be less than 1, basically in between 0 and 1. So in between 0 and 1, and we'll talk about negatives later on. But if you have a B that is greater than 1, you have growth. If you have a B that is less than 1, you have decay. All right? You can actually look at the function and determine. I am going to look at this function without graphing, determine whether the function represents growth or decay. And so if I look here, my B is the one that is the base of the exponent x. What is my B here? Is it less than 1 or greater than 1? Yeah, it's a decimal. So that means this guy is decaying. It's getting smaller. All right, you're taking a fraction basically to a power. It's getting to be a fraction with a bigger denominator, which means the denominator is growing and your numerator is not, right? And so it's getting smaller. So let's look at these together without graphing. Look at this first one. 100 times 0.12 to the x. Growth or decay? Decay. What about B? Growth. It is a 5. What about C? Decay. Very easy. All right. And then they introduced this term here. An asymptote is a line that a graph approaches but never reaches. All right. So this is basically a dotted line that you don't actually have as part of your graph. And you are approaching it, but you're never actually going to get to it. If you look at this one, with exponential functions, they usually shoot way up and they get closer and closer to this line here and they never actually touch it. They don't go over it, they just keep getting closer and closer to it. And that's why it continually curves up to where it almost looks like it's perpendicular, but it's not. It's actually just getting infinitely close to a line. All right, let's look at depreciation. Look at depreciation. All right, so if you look at page 426, page 426. So let's look here. It says depreciation. When you're talking about depreciation, is the decline in an item's value when resulting from like age or wear and tear. And so a good example of this is a vehicle. All right. The exponential decay graph shows the expected depreciation for a car over 4 years. Estimate the value of the car over 6 years. Okay. And what you'll see with cars is it's not going to go, obviously value will never be in the negative, right? That doesn't make sense at all. But you will see it plateau a little bit with something like a vehicle. And so you'll depreciate exponentially, and then it'll kind of even off a little bit. And so that's why you see this type of decay with a car. After so many years, it's pretty much going to hold its value at a very small amount unless it's just not running at all, and then you can sell it for parts. But it's going to decay like this. So it says, estimate the value of the car after 6 years. So the first thing we're going to do is we are going to look at an initial value and a final value, and we're divided by by the initial value. That's going to be our percentage of decrease, right? And so the initial value then was how much? How much was our initial value? 20,000. And then they are going to look at it at the, I think they did it at 17,000, right? So they must have done it after what? Just 1 year? After just 1 year? They must have done this guy right here. So we're going to say, well, we are now worth after 1 year, we're worth 17,000. We were initially worth 20,000, right? And if we divide that by 20,000, we will get, if you divide it out, negative 0.15, negative 0.15. All right. My B, remember when we calculated the B with the 1.24%, right? 2 point, whatever that, we need to add it to that. So add, and this is already in decimal. It's not in percentage at this point. So if it was in percentage, we'd have to change it, but it's not. It's already in decimal. All right. So we have an ending value of 17,000, an initial value of 20,000. We subtracted and divided by our initial value. We got the negative 0.15. Remember, our B is always 1 plus it. All right, 1 plus. Even if it's negative, we're going to add 1 to it. So what is our B? 1 plus negative 0.15. That's 0.85. So if my B is 0.85, it is less than 1. We have decay, which is what we're talking about, right? Decay. Now, my initial value, so if I were to set this up in an equation, y equals a b to the x, all right? My initial value is always my a, all right? So I can calculate my initial value using my 0 and my 20,000, or if they tell you it's the initial value, you don't have to plug it in. What was my initial value here? 20,000. So I don't even have to do, x is 0, y is 20,000. If you have your 0 amount, like we had our 2000, our starting 0 year, then A is always going to be the initial amount that it was in that starting year, okay? So I don't even have to plug in my X and Y. If you know your initial amount, you can go ahead and plug that in for A, all right? So I can say, I know my initial amount was 20,000, right? And then I just figured out what my B was, so I actually have my equation here. My initial value and my B is really all I need to set up an exponential equation. Initial value and your value of your growth or decay, B, okay? So I have it. So how do I predict it after 6 years? Well, X represents my years, Y represents my value. If I want to know the value after 6 years, where am I going to plug it in? X. So after 6 years, it should be 20,000 times 0.85 to the 6th power. So go ahead and calculate that. So $7,542.99 to be exact. All right. Go ahead and calculate it after 10 years. E is actually called E because it's called Euler's number sometimes. Euler was a mathematician in what, the 1700s? I'll have to look it up. Anyway, he's credited with this. It was actually used before that, but when we start talking about logarithms, which is what we're going to do this particular chapter, E comes into play. They explained it a little bit if you look at the top of the page. E represents the asymptote that is represented by the function 1 plus 1 over x to the x. So when you have this crazy function 1 plus 1 over x to the x, you get this little number on your graph, which is E. It is a non-repeating, non-terminating decimal. You have been introduced to a non-repeating, non-terminating decimal that you use a symbol for many, many times. You've used it all the way back to at least Algebra 1. What is a non-terminating, non-repeating decimal that you've used? All right, so another little guy that you are familiar with is this one right here, 3.1415, whatever, and it keeps on infinitely, right? This little guy is estimated at 2.718, and it keeps going infinitely as well. In your calculators, you have him. All right, so they show you a graph of E, and they're like, estimate the value of E based on the graph. No, we're not going to do that, because in your calculator, you have him, right? Yes. And so if you have to use the calculator to graph him, you might as well just use the calculator to calculate him, okay? And so if you look on your calculator, you should see LN, and above that LN, you see E to a power, E to X, all right? And so if you use your shift or your second button, you should get your E, and it'll automatically be to a power. And so we are going to go through these and just make sure you know how to use your calculator with E, all right? So E to the fourth. If you're calculating E to the fourth, you should put your second E and put it to the fourth, close it, enter. One of the most common ways that E is used is with compound interest, all right? Compound interest. And so talking of earning money versus paying money, all right? Compound interest is tremendously good when you're earning money. It is tremendously bad when you borrow money, okay? So basically what compound interest does is it takes the money. So let's say we're going to talk about investment because we're not going to actually take out a loan. We're going to have investment, all right? You take money and you invest it. If they compound annually, that means every year, let's say you earn 10% on your money, okay? Every year, so you invest $1,000. What's 10% of 1,000? So at the end of the year, they give you $100 with that 1,000. Compound interest then takes $1,100, and now you're earning money on $1,100. Okay. Nice. And so the more often it is compounded, the more money you would make. So if they compound it every month, it's much nicer. Which is, by the way, what credit cards do. They compound every month. All right. And so when they compound every month, then they're gonna earn more money on your money plus the interest they just earned on your money. Okay. And so that's what they're doing. And so this is when you compound continuously, okay, continuously. So that means it is continuously compounding interest, continuously, not weekly, not monthly, not annually, continuously. And so this is the formula that happens when you compound continuously. Let's talk about the pieces of this formula, all right? The A represents how much money you have in the account, all right, after you have earned all your interest. The P represents the principal or the initial amount that was invested. The R is the rate of return or your interest rate that you're earning. And the T is the time, specifically in years, It's easy to remember because it looks like the word PERT. Y equals PERT, all right? So Y equals PE to the RT. You'll notice that E is your base, your natural number base for continuously compounding. RT is a product in your exponent form there, okay? R times T. So let's look at how this works. Suppose you invest $1,050 at an annual interest rate is 5.5% compounded continuously. How much will you have in the account after 5 years, all right? So we have A is what we're solving for. Our initial amount, that's our P, 1,050. Times E to the R. Our interest rate is 5.5%. How do I write that then? 0.055. Yep, 2 decimal places over. So I'm going to take that 5.5 and move it over and fill in a 0. So 0.055 times how many years? 5. 5. So in your calculators, you want to do 1050 times E, and it's going to automatically open when you do that E, to the 0.055 times 5 in those parentheses, all right?